Welcome to Hart and Trocken. My name is Dirk Schiebon, and in this video we talk about the idea of definite integrals. A definite integral is a way to calculate the area between the curve of a given function f, the x-axis, and two vertical lines called the limits. At the same time, definite integrals establish a very fundamental relationship between calculating areas under curves and the idea of differentiation. Actually, that relationship is one of the most fundamental relationships in mathematical calculus. So let's see what that is all about, and let's go. We start our story with this function. We call this function f, and its formula is in fact f of x equals sine x plus 2. However, its precise formula is not of much interest to us. We are rather interested in two properties of this function, and that is that the function is non-negative, that means its graph is above the x-axis, and that the function is continuous. That means it doesn't have any jumps. Apart from being non-negative and continuous, this function could be just any other function. Now, based on this function, I want to build a new function, and that is the so-called area function. Let's see what an area function is. First, we fix some number a on the x-axis. Let's say we choose a equals 1. On the right side of a, we choose another point, which we call t. We now mark the area which lies between f, the x-axis, and the two vertical lines which go through a and t. We are interested in the value of this marked area. We now think of a and t playing different roles in a sense that we think of a as a fixed constant, whereas we think of t as a variable number. That means a variable which can assume different values. Accordingly, the orange area can vary depending on the value of t. That means it is a function of t, and we call it capital A of t, where A stands for area. So if we change the position of t, the function a of t assumes different values. Now let's reflect a little what we just have done. From a given function f of x, which is non-negative and continuous, we have created a new function, a of t, about which we know that it describes the area between f and the x-axis between a and t. The typical thing which we do in mathematics whenever we have created something new is to collect properties. Because f is non-negative, one property is quite obvious, and that is that a of t is monotonically increasing. In other words, the area increases whenever we increase the value of t. A second, also very obvious property is that a of a is 0. In other words, if we move t to the point a, we have no area. The next property we collect is a little harder to prove, but is one of the most important results in mathematics. It reveals a very close relationship between differentiation and area functions. In fact, we want to find out what the derivative of our newly created area function is. Usually, when thinking of derivatives, we think about slopes of tangents. In this case, however, we can't think of a tangent because our function a of t is not given as a graph. It is rather given as the area beneath the graph of another function. So the way we think about derivative here is to think about rates of change. Rate of change means that whenever we have a given position of t, for instance such as t equals 2, we want to understand by which amount the area a of t increases if we move t a little tiny bit to the right. Of course, that is loosely spoken, so we have to put that into precise words. I want to do that both with formulas and with graphical illustrations. The formula way to do it is to express the derivative of a of t as a differential quotient. Remember that the differential quotient of the function a of t would look like this. So if we calculate that limit a of t plus delta t minus a of t divided by delta t, we have the derivative of a at the point t. As we have defined our area function a only graphically right now, we want to graphically understand what this quotient is, or what that limit of these quotients is. Let us begin by understanding the denominator, delta t. We can think of delta t as a tiny positive number by which we increase t. In order to have a nice illustration, we reinterpret tiny to be 2 and set our point t plus delta t at 4. Don't worry, that doesn't make any difference for our result, it's just a nicer illustration. The important thing to note is that the length of the segment between t and t plus delta t is of course delta t. So that is the graphical illustration of the denominator above. Now, what is the numerator? It is a of t plus delta t minus a of t. But a t plus delta t is the area under the function between the point a and the point t plus delta t. So in fact, it's the entire area which is composed by the orange and the yellow part. The other part of the numerator, a of t, is of course the orange part. So the difference of those two is exactly the part which we have colored yellow. So the differential quotient above can graphically be thought of as the yellow area divided by delta t, which is graphically the width of that yellow area. Now, to be precise, we are not interested in any of these quotients at all. We are only interested in the limit which these quotients approach when we let delta t tend to 0. Graphically, we would like to understand which limit this quotient tends to when we do something like this. Now, in order to answer that question, we use a little trick where we compare the yellow area with two very simple rectangles. The first rectangle is this one. The height of this rectangle obviously is f of t, whereas the width of this rectangle is delta t. So the area of this rectangle is f of t times delta t. Obviously, the area of this rectangle is greater than our original yellow area. That means it is greater than a of t plus delta t minus a of t. Next, we compare our yellow area with this rectangle. It has the height f of t plus delta t and the width delta t. So its area is f of t plus delta t times delta t. Now obviously this rectangle is smaller than our original yellow area, which is why we can put a greater than or equal sign here. Okay, let's pause a second. By comparing our original yellow area with two rectangles, we have derived this double inequality. And this double inequality turns out to be very valuable to us in order to calculate our differential quotient. Because the first observation is that the relation between the areas of the rectangles and the yellow area will be preserved when we let delta t tend to 0. We can illustrate this by showing both rectangles and by letting delta t tend to 0 again. You see how that relation is preserved. One of them is always smaller and one of them is always bigger than our yellow area. By the way, if you follow along closely, you might have noticed that there might be situations where the relationship is not preserved. These cases would occur if the blue function f of x would switch from decreasing to increasing or the other way around. But in fact, it will turn out that that does not interfere with our final argumentation. So we can keep the situation as simple as here. Now the first thing which we do is to take this double inequality and divide every expression by delta t. By this, the delta t factors of the right and the left expression will vanish, and in the middle expression we will have a delta t in the denominator. Now observe that the expression in the middle is almost the quantity we are interested in. The only thing which is missing is the limit operator. But because we said that the relationship is preserved when we make delta t small, we can put a limit operator in front of each of the three expressions. We say that these relationships are preserved in the limit. Now, seriously, in my opinion, what we're doing here is one of the coolest things in mathematics. We are building up a rigid, elegant argumentation which demonstrates once and for all a mathematical truth on a very general level. Well, let's continue. Well, first we observe that the expression in the middle is exactly the derivative of a at t we are interested in, so we can replace it by a dash of t. And the big showdown is now that the expression on the left-hand side is nothing else than f of t. Well, because it's a constant sequence, f of t, it does not depend on delta t. So we can replace the left-hand side by f of t. So what remains is the expression on the right-hand side. We want to have the limit of f of t plus delta t when delta t tends to 0. Now we have to use one of the properties we have demanded of f in the very beginning, namely that f is continuous. Because f is continuous, we know that when we have a sequence tending to t, that then the sequence of the function values of this sequence will tend to f of t. And here we have a sequence which tends to t. This sequence is t plus delta t, because delta t is a 0 sequence. So by the continuity of f, we know that the right-hand side expression is nothing else than f of t as well. So that's what we have found. What does that say to us? Well, it's a double inequality which says the quantity we are interested in, a dash of t, is smaller than or equal and at the same time greater than or equal f of t. Well, there's only one possibility left in that situation, that it is exactly equal to f of t. So that is the last change we do here. We replace the complete inequality by a dash of t equals f of t. Well, now you might think, why is he so excited about that little fact? Well, because the implications of this insight are enormous. Remember that a is the area function under the graph of f. That we have chosen f to be sine x plus 2 is just one random choice. We could have chosen any other non-negative continuous function f. For all of these functions, we could have shown, using the exact same way of argumentation, that the derivative of the area function under the function f is exactly the function f itself. That is a fundamental truth and establishes a fundamental relationship between functions f and their area functions a. In fact, there is a way to think about that truth which makes it not surprising at all. And that is the salami idea. If we think of the area function as a salami, and if we think of the function f defining the shape of the salami, it is not surprising that at a given position t, when I slice the salami, the local rate of change at t, that means the size of an infinitely thin slice of the salami, is defined by the diameter, or more general, by the shape of the salami at that position t, and that is by f of t. Now the thing is that we can use this insight for calculating areas under given functions. That means we can, for instance, calculate this orange area, which is the area between f and the x-axis, ranging from a equals 1 to t equals 2. How can we do that? Well, from our insight, it follows that a of t is an indefinite integral of f of t. In other words, a of t is an antiderivative or a primitive of f of t. Now we use the fact that any two indefinite integrals of a given function f only differ by a constant c. So suppose we are given any antiderivative of f, which we call capital F, then we know that capital F and a only differ by a constant c. Now, the funny thing is that we know something about that c, because remember from our earlier properties, we have found that at the point a, our area function a is equal to 0. So if we now take the equation a of t equals f of t plus c and plug in a for t, we get 0, which is a of a, equals f of a plus c. And if we now solve for c, we get c equals negative f of a. Now, if we plug this value for c into our earlier equation, a of t equals f of t plus c, we obtain an extremely important result. It is a formula of how to calculate the area under a curve between the left border a and the right border t. Actually, the difference capital F of t minus capital of a is so important that it is worth being given a name and a notation on its own. It is called the definite integral of f with a lower limit a and the upper limit t. And the interpretation of it is exactly the orange area. That means the area under the curve of f ranging from a to t. So let's define that properly. If we have any function f for which we know any of its antiderivatives, or in other words, any of its indefinite integrals, which we call capital F, and if we have a closed interval ab such that f is defined on that interval, then the quantity capital F of b minus capital F of a can be interpreted as the area between the function f, the x-axis, and the vertical lines at a and b. We call that quantity the definite integral with lower limit a and upper limit b. And in fact, there are three different notations of this definite integral. The first and the most important one is this one. Observe that the only difference to the notation of the indefinite integral is that here additionally the limits of the integral are written beneath and above the integral symbol. So from now on, whenever we see a notation like this, we know that we are supposed to calculate the area between f and the x-axis with a lower limit a and the upper limit b. Then there are these two equivalent other notations, which involve capital F instead of f. They basically mean the same thing, but they are typically used in situations where we already know the antiderivative capital F. So that is the definition of the definite integral. Actually, there's one thing which we haven't discussed yet, because in our earlier considerations we have restricted ourselves to functions f which were non-negative. However, the function f of course also should be able to be negative. So how can the area between the graph of f and the x-axis be interpreted when f is negative? In this example, we have a function f of x which is both above and beneath the x-axis in different sections. Then, if we calculate the definite integral with limits a and b, the parts of the function which are above the x-axis contribute a positive value, whereas the parts which are beneath the x-axis contribute negative values. So for instance, assuming that the two middle parts have roughly the same area, they will approximately cancel out each other and altogether contribute a value to the integral which is near 0. The same is the case for the two areas at the very left and the very right of the figure. So the definite integral of this example should be close to 0. On the other hand, if we are interested to calculate the sum of the colored areas without any negative contributions, we have to split the integral into different intervals and make sure that the integrals of the negative parts are equipped with a negative sign such that they will also contribute a positive value. The same is achieved if we equip f itself with absolute value bars, thus flipping the negative parts of the function vertically along the x-axis. Let us calculate some examples. We first start with a very simple one. We want to calculate the area under the graph of the function f of x equals x squared. We want to do this with lower limit 0 and upper limit 1. According to our earlier results, we simply have to find any antiderivative of f of x. One example is 1/3 times x to the third power. We now can calculate the definite integral of f squared from 0 to 1. Using the notation which involves the antiderivative, we have this, which can be calculated as the difference of the antiderivative evaluated at 1 minus the antiderivative evaluated at 0, which in this simple case is 1/3. Let's do another one. We want to calculate the definite integral of the function e to the power of 2x from 2 to 5. The first step is to find an antiderivative of e to the power of 2x. A simple example is 1/2 e to the power of 2x. So the integral is equal to, which in turn is equal to 1/2 e to the power of 2 times 5 minus 1/2 e to the power of 2 times 2. This can be simplified a little to 1/2 times e to the power of 10 minus e to the power of 4. And we do another one. We want to calculate the area under the function x minus x to the third power minus x to the fifth power from -2 to 2. To find an indefinite integral, we can use the splitting rule for sums of functions. So the antiderivative is 1/2 x squared minus 1/4 x to the power of 4 minus 1/6 x to the power of 6. Plugging in the upper limit, we have 1/2 2 to the second power minus 1/4, 2 to the fourth power minus 1/6, 2 to the sixth power minus, in brackets, 1/2 -2 to the second power minus 1/4 -2 to the fourth power minus 1/6 -2 to the sixth power. If we do the math, we get 2 minus 4 minus 64 over 6 minus 2 plus 4 plus 64 over 6. And that results in 0. So according to our calculation, that definite integral is 0. Why is that the case? Well, by the formula and by looking at the graph, we notice that the function f is a so-called odd function. That means a function which is symmetrical to the origin. And that means that whenever we calculate a definite integral with symmetrical limits, that means negative a and positive a, we have to get the result 0. And that is the case here when we calculate the integral from -2 to +2. We do a last one. We calculate the definite integral of sine x from 0 to pi. An antiderivative of sine x is minus cosine x. So plugging in, we have negative cosine of pi plus cosine of 0. Now cosine of pi is -1, whereas cosine of 0 is +1. Taking into account the two negative signs, we have 1 plus 1, which is 2. At the end of this video, we quickly collect some properties of definite integrals. The first property tells us what happens if we interchange the limits. That means if we swap a with b. By using the definition of the definite integrals, which is the difference of capital F of b and capital F of a, it is immediately clear that interchanging a and b leads to a negative sign. This property is especially useful if we have a situation where a is greater than b. That means where the lower limit is actually greater than the upper limit. The next property, which is both an immediate consequence of the above property and which also stands for itself, is that when we integrate from a to a, that the result is 0. If there is a constant alpha involved in the function, we can pull alpha in front of the integral. And finally, if we integrate a function from a to b, we can split up the interval ab into two intervals ac and cb and calculate the integrals for these intervals and finally adding up the results. This is nothing else than splitting up an area under the function into two partial areas, one ranging from a to c and the other one ranging from c to b. So that was our story about definite integrals. Thanks for watching and see you next time.